Look closely at the inside of this system. It uses high-grade 316L stainless steel and continuous UV sanitation, filtering water to absolute ultra-pure standards. This graph tracks microbial counts inside a standard pharmaceutical water loop. The colony-forming units sit near 0 for the first 5 months. Then, at month 6, we see a massive, inexplicable spike in contamination. The immediate assumption is that a breakdown in chemical treatment or a defect in the metal caused the breach. We assume that top-tier materials and active filtration mathematically guarantee a sterile environment. The problem is that stationary defenses, like a UV lamp or an ozone generator, only treat the water passing directly through them. They offer no protection against localized bacterial colonization happening miles down the pipeline. Maintaining a sterile distribution loop requires looking past the chemical composition of the water. We have to look at the physics of how that water moves. To prevent biofilm formation, engineers must build an active kinetic defense system. That requires manipulating a specific metric known as the Reynolds number. To see where the system fails, we need to zoom in on the microscopic fluid dynamics occurring right at the internal wall of the pipe. This animation illustrates laminar flow. The water moves in smooth, parallel layers, creating a parabolic velocity profile. Notice the edges where fluid meets metal. Friction acts on the water, dropping velocity to exactly 0. Because the water is stationary here, bacteria easily adhere. Without kinetic force to wash them away, they multiply into a resilient biofilm. This equation is the Reynolds number, a ratio of inertial forces to viscous forces. To calculate, multiply fluid density by water velocity and pipe diameter, then divide by dynamic viscosity. Below 2000 is dangerous laminar flow. 2000 to 4000 is transitional. Above 4000 is turbulent flow. Global health authorities require pharmaceutical loops to maintain a Reynolds number above that 4000 threshold at all times. However, best-in-class pharmaceutical engineering teams design their main loops to run well above 10,000 to maintain an absolute margin of safety. Pushing this metric high enough forces the water to stop acting as a passive carrier and start acting as a physical scrubbing instrument. This rapid transition from smooth layers to chaotic swirling eddies introduces the first mechanism of turbulence, shear stress. These eddies crash against the boundary layer. The kinetic energy physically scours the internal metallic surface, stripping away microscopic contaminants long before they have a chance to anchor. Beyond kinetic force, turbulence ensures the success of uniform heat sanitization. This thermal gradient map shows an 80 degrees Celsius sanitization cycle. In a laminar profile, the stagnant boundary layer insulates the wall, creating cold spots where bacteria survive. In the turbulent profile, constant mixing ensures perfectly uniform edge-to-edge heat across the entire pipe. The same principle applies to chemical distribution. Even highly polished steel has microscopic abrasions. Turbulent flow physically drives sanitizing particles deep into those tiny crevices, ensuring the chemical agent reaches every biological hiding spot. Increasing water speed is a means to an end. Powerful turbulence is the required delivery mechanism that allows heat and chemical sanitation to effectively sterilize the pipeline. Knowing the theory is only half the problem. Process engineers must actively manipulate system variables to guarantee the Reynolds number stays in the turbulent zone. The most direct lever we have is fluid velocity. The industry standard target is to push water through the loop between 1.5 and 2.1 meters per second. This control dashboard demonstrates another major lever, heat. Because temperature and viscosity share an inverse relationship, raising the water temperature lowers its dynamic viscosity. As that denominator shrinks, the output gauge for the Reynolds number is driven exponentially higher into the green turbulent zone. To maximize the effectiveness of this flow, the internal pipe surfaces must be electropolished to a surface roughness of less than 0.6 micrometers. We strictly need chaotic flow, but we require that dynamic chaos to be generated entirely by high velocity. If turbulence is caused by internal surface roughness, those structural imperfections will simply act as permanent traps for bacteria. Even if the main loop maintains perfect velocity and temperature, the entire system can be compromised by a single architectural feature, the dead leg. In this T-junction diagram, the main line maintains high-velocity turbulent flow. Inside the capped branch, velocity drops to zero, neutralizing hydrodynamic defenses. Engineers follow the 2 to 3 rule. Branch length cannot exceed 2 to 3 times its diameter, or the flow isolates. A perfectly tuned high-velocity distribution loop is only as sterile as its most stagnant point. A single unregulated dead zone provides bacteria a safe harbor to multiply and contaminate the entire continuous system. Translating these physical parameters into an operational facility means proving them to regulatory bodies like the FDA or the World Health Organization. In a real-world facility, operators constantly open and close valves at various user points. Every time a valve opens, the system experiences an unpredictable pressure drop, which directly threatens the velocity of the main loop. To counteract this, modern loops rely on variable frequency drives, or VFVs, to actively manage the pump speeds. This piping and instrumentation diagram tracks that process. When a user valve opens, the resulting pressure drop is detected by a flow meter. That meter instantly signals the VFD, which ramps up the main pump's RPM to stabilize the flow rate, ensuring the Reynolds number never dips below 4,000 even during peak demand. When an auditor reviews the facility, they look for exactly this data. They expect continuous velocity logs, verifiable dead-leg dimensional tolerances, and detailed Reynolds number calculations, modeled against worst-case usage scenarios. Regulators do not assume sterility simply because expensive equipment was installed. They require continuous mathematical proof that the system maintains exact hydrodynamic performance thresholds. A compliant high-purity water loop is a kinetic defense system. By maintaining rigorous mathematical control over the Reynolds number, engineers actively build sterility into the physics of the flow.